Raiders CubeSat Design Review by Maddie, Ryan, Jaime, Ali, and Gonzalo.
From left to right, Ham, Gonzalo,
Ali,
Jaime,
Ryan,
and Maddie.
For the system level block diagram, we decided to implement the smart requirements in the overall picture in order to make it more clear. Such as you can see here in the structures subsystem, for example, you can see that the smart requirement for the subsystem is the overall structure shall contain all elements needed for the final demo. The elements would be the battery, the camera, IMU, etc. Then for the power system, our smart requirement was that the battery is fully charged and solar panel is charging adequately, meaning that everything's working and like for the power subsystem to work in our final project demo. Then for the command and data handling subsystem, we have Raspberry Pi microprocessor runs Python code and controls subsystems correctly. Then communications, we have Raspberry Pi is able to downlink to the ground station. Doesn't matter through Bluetooth or Wi-Fi, SSH, yeah. Then imaging, we have the smart requirement is that the camera shall take accurate and clear photos. So, for example, we can take a photo before running the demo to see that if it's working correctly. And then lastly, for the ADCS subsystem, we have attitude and motion sensors are working. So those are the smart requirements. And in the overall diagram, you can see that we have a lot of lines connecting each thing, like the acrylic walls connecting to the solar panel brackets. Solar panel connects to the battery because it's what charged the battery. Then we have a lot with the heart of the diagram, which is a Raspberry Pi microprocessor, which connects to all of the communication subsystem parts and the ADCS subsystem and the imaging subsystem. Which is the main idea here that we're trying to get is that it all goes through the Raspberry Pi microprocessor, which ultimately takes it to the ground station, which is the downlink from the Raspberry Pi.
At first, the satellite will begin as off, and once it is switched on is when the pre-launch phase begins. In this phase, we'll check if the solar panels work, if the battery is charged, and if the cameras work. And we'll check this out as well by seeing if the Raspberry Pi turns on. If everything is okay, we can continue back to the pre-launch phase and move on to the launch and orbit insertion. The satellite will be held by hand in a low Earth orbit about 3 feet above the ground. It will be moved around the house to detect plastics that would portray plastics in the ocean. We will then move on to the self-test phase. We will see if the CubeSat can detect plastic. To validate this, we will make the CubeSat, we have coded it so that once it detects a plastic, it takes a picture of it and it uploads it onto Twitter, onto an account that we've made. If it fails, we go into an error contingency phase, and then if that is resolved, meaning that if it is able to upload the picture onto Twitter, then it is resolved and we are on to our last phase on orbit on station. If it stays on error contingency and fails, it will be a failure and we'll go back to phase 1, which is the off phase, and restart everything.
CAD model or mechanical drawing. What you're looking at here is an outline or model of our final prototype. The side panels consist of one acrylic side panel and 2 side brackets attached by 256 screws. The 2 L brackets attached to the top and bottom of each of the middle holes in the side panels are connected by 440 screws, and those L brackets face the middle of the CubeSat and are perpendicular to the side panels. The side panels are connected to each other by 256 screws, and the side panels with the same side bracket are opposite each other. The top and bottom panels are connected through side panels using the L brackets with 440 screws.
Inclusions to the slide above. On the left, we have a photo of the power bank. Then in the middle, we have the Raspberry Pi, IMU, and then on the right, we have the camera. These would all go into our prototype, as shown in the CAD model, mechanical drawing.
Mass, budget, and bill of materials. So in order to find the cost per unit for each of the materials, we were able to look in the boxes that they came in, and for most of the time, you were able to find the brand that they were from, and look at the cost of those. For the ones that we were not able to find the brand for, or they were hard to find online, we were able to find similar parts, and from different brands, we'd averaged them out and found an average cost. So we put that for the cost per unit. So our total cost came to be about $243.77, and we added a margin of plus or minus $35 just because we're not completely positive on those numbers, and also in case we add parts. For total mass, we had about 512 grams. It was difficult to find mass online for each of the objects. We were only able to find weight if we were even able to find weight. So what we did is we found the mass of more common objects or everyday objects, and ones that seemed like they would have more similar mass to the Raspberry Pi and satellite. And from there, we got 512 grams with a margin of plus or minus 100 grams.
For the power budget, the Raiders team was instructed to find the estimated charging and discharging time plus the power consumption of the power subsystem. To find the estimated charging time for the Raspberry Pi, our group left the battery outside plugged into the solar panel on a sunny day. The battery took a total of 3 hours and 26 minutes to fully charge from 0%. For the expected discharging time and power consumption, we left the battery plugged into the Raspberry Pi. For the first test, we left the computer running without using it and leaving it idle, and got a rate of 2 minutes and 25 seconds per 1 battery percentage decrease. For the next test, we roamed the internet on the Raspberry Pi and saw a 50% decrease from the first test. The rate stood at 1 minute and 20 seconds per 1 battery percent decrease when roaming. Conclusion: the power consumption depends solely on the amount of usage happening on the Raspberry Pi. Additionally, we did not account for the fact that the solar panel could technically charge the battery while taking photos, as this does not apply to our specific simulation. Our simulation will take place inside, therefore leaving this not a factor that comes into play. In the situation where the CubeSat would be launched into space, this would be an important factor to take note of, but in our case, it is not. Here we have the software architecture slide, which is a transition in between states for our CubeSat. We start at the ground station, which will initiate all subsystems as a start. After that, the function will begin, which is identifying plastics in the ocean, which in our case will be inside of our home in a 120 square foot area. Then we will reach the image detection loop, which is the loop that is detecting plastics all over the area we are lifting the CubeSat over. So if an image candidate is identified, it will be compared with a library of plastics. If the image does not match, it will go back to the image detection loop to detect more plastics. If the image is matched, however, the image will be captured and the image will be stored with a timestamp, image name, plastic type, plastic location, and plastic estimated size. After the image is stored, it will be sent over with Bluetooth, and the image and data will be stored in the ground station. Then we added an extra step, which was tweet image using Tweetbee library, which was something we implemented by ourselves to differentiate our group from the others. Then with the image on Twitter, we will continue to go back to the image detection loop to detect more plastics until stop is pressed and the system will go idle. For the software development plan, we made a diagram of phases plus examples to connect to each phase. For the first phase, planning, an example would be roles and work stream distribution. So we would be planning the design and how we're going to implement each subsystem to our final demo. Then going down, we go to requirements gathering. We have another arrow going back to planning in case there are bugs or something we need to fix in order to replan and assess our situation. For the requirements gathering, an example would be tweet images in scope, identification of ships out of scope. Going down, we have functional specifications. This could be types, shapes of plastics that we want to identify, such as bottles or cardboard or, like paper. After functional specifications, we go down to technical specifications, which would be something like Python libraries or packages that we need, such as the one that we used for the Twitter. Going down to development, we also have an arrow that goes from development to technical specifications because development has to do with coding and Python coding. So if the coding is off, we can go back to the Python libraries and reassess and use another Python library package that we would need for the coding. After development, we go down to testing. Testing could be unit tests, integration tests, UAT tests, which also has an arrow back to development in case we have to recode and assess the bugs. After testing, we go down to deployment/demo. This could be multiple flights, so we do multiple demos to see how it is and assess how we can change the flight if we have any issues. And then lastly, we have the backlog prioritization, which is just a question that we're going to ask is what do we implement next to move on with the final presentation and demo. For the link budget test, we use the Bitwise application through SSH to test the time the Raspberry Pi took to downlink a normal file to the ground station. For this test, we took one of the photos from our FlatSat challenge and tested to see how long it took for the Raspberry Pi to send the photo to the ground station computer. With this data, we found that the data rate was 1.44 megabytes per second through the SSH connection. We claimed that the link will not change throughout our test orbit final demo because there are no relevant differences in the data rate throughout the test unless we leave the house. That would mean that we would have to use Bluetooth connection instead of SSH, which is not what we are intending to do for our final demo.
For our data budget, we came to the conclusion that our CubeSat is going to downlink only the amount of photos that have plastic detected. That means that only the photos approved by the Python libraries will be sent to the ground station and posted on our Twitter development account. To give sort of a perspective, around each photo is 3 to 7 megabytes and we have 8 gigabytes of free space. For the integration and test plan, our team will combine the work that we each did for the design review to move forward and get the demo started. Ultimately, taking photos of plastic in the ocean is impossible in our circumstance, so for our demo, we will lift the Raspberry Pi 3 feet and move it around an area of about 120 square feet. To test to see if our demo worked, we will check the files to see if the pictures were correctly taken and downlinked to our ground station. Our team will use the experiments we each did with the subsystems to reach our own goal for the final project. Additionally, we will check our Twitter account, which is shown on the right, to see if the photos were uploaded here as well. Our team will implement code using Python libraries and SSH connection in order to make this happen. We think that the Twitter account will separate us from the other groups and help improve the realism of our final project. We were also thinking of coding another library that will be able to detect boats. This is interesting because if we detect boats, there could be a message sent to them stating that there is plastic nearby. This download would be good for the environment, and it is a creative way of extending the final project requirements.
Thank you.